Good morning, everybody. I was invited here to talk a little bit about my research, but also give an overview on smart grid. But before starting what I'm going to say, I wanted to just let you know that this quarter we are starting a smart grid seminar at Stanford, where we are inviting faculty and researchers from other institutions to come and spend the day at Stanford giving a seminar and also meeting with students afterwards. So you're welcome to enroll to this course or attend the lectures, and we're going to have really exciting speakers like Professor Felix Wu or Marija Illich and so on. So if you're interested in this class, please email me or some of the other organizers. You should see information about it circulating soon, and it's sponsored by the Tomcat Center. Okay, so what I want to do today is kind of, the topic I was asked to talk about was smart grid plus storage. And I was thinking about it and trying to see what these two things have in common and why, in fact, they form a really nice pair and they lead to many interesting questions that we need to answer. So what I want to do is just give you a very quick introduction about smart grid and what I think about it, which is the notion of an architecture for managing resources of new types. Then I want to go into controlling this new smart grid and explain to you the role of storage. At the end of the talk, I want to show you how we can use some existing data to evaluate and design some of these systems. So California set pretty aggressive greenhouse gas reduction goals. So 1990 levels by 2020, 33% RPS, and then 80% reduction by 2050. And the state put out a report saying, meeting these goals requires a multitude of approaches. You need to move various sources of energy consumption into electricity, and then to make that electricity low on greenhouse GHGs, you need to be able to add renewables to generate the electricity. Now electricity coming from renewables is intermittent. Therefore, we need to be able to do zero emissions load balancing. And together with all of these three, overall, you want to achieve energy efficiency to reduce the total consumption. So, as we know, as I mentioned to you before, here you can see renewable generation, and it's highly variable. So you really need to focus on this part. So here's my way of thinking about this problem, okay? And I think it's part of the community as well. So I think about it as a resource management problem. In one side, I have constraints given by electricity markets, the power network, the communication that you can have with different devices in the grid and different generators and resources, and also the sensing and information that you can obtain. On the other side, you have the resources that you can effectively use to do this management. Storage, demand response, loads, charging, etc. And the key here is to figure out an architecture, algorithms, and data processing to make this problem manageable and efficiently solved. Okay? So just very quickly, I wanted to show you, what the grid looks like today. It's kind of this hierarchical system where generation sits at the top and the system operator sits here. He makes a decision of who is going to generate what based on predicting what these loads are going to do. Okay? And information flows from top down. Here, this is what people are saying the distribution system will look like tomorrow. You have the same end-use appliances in homes and so on, but you have more opportunities for communication. You have new devices attached to the distribution system, and possibly a lot more information coming in, which makes it very hard to manage your grid in this way. So a concept we have been exploring at Stanford is this notion of re-architecting the grid and thinking about your distribution network as small clusters. Each of these clusters you can perhaps manage in this way. Clusters coordinate across themselves in an autonomous way. And the system operator now can look at his infrastructure and determine a core grid and then be comfortable in the notion that these guys all try to self-balance in a way. Okay, so in a very high level, this is it, and you can formulate it mathematically. So what is this cluster idea. So here is my conceptualization of what a cluster is. So it's all of the loads. So those are residences and businesses and so on in a particular region, as well as all the resources that are available for this cluster to balance loads with the supply. So this guy has some solar, has some local generation. He has the capability to defer loads and so on. Now the net energy from this cluster is purchased in your standard electricity market. And here is just a little cartoon of how the electricity market works. Because generators need to be dispatched in advance, the market is run 24 hours ahead. All your net load from your cluster is predicted, and based on that, power is scheduled here. Obviously, your forecasts are not correct, so you have some updates, and then adjustments are made on what's called ancillary services or reserve markets, okay? So our notion of a cluster is a guy who interfaces to the market and has all these resources at their disposal. And here is just to illustrate what happens in the forecasting. So in the dotted line here is the actual net load, which I'm just saying is the actual load minus solar. And as time goes by, you get closer and closer to the actual prediction over the hours. Okay. So the way this management is done today by the grid operator is called worst case dispatch. Basically, they take your forecast, they say, what's the worst case error, or the 3 sigma, if you are familiar with Gaussian distributions, and say, I'm just going to allocate that much power. Clearly, that's extremely conservative, and as we have more and more renewables and more variability, that amount of extra allocation is going to grow and make it infeasible to use this strategy. So what we propose for our clusters is what we call the risk limiting controller, or dispatch. And the goal of the controller is very simple. He has a price for power at different times according to the market, and then he has a net load that he needs to satisfy, subtracted of the total amount of power he has contracted. At each time, he can take a decision based on the information available at that moment. So this turns out to be a dynamic program, and you can find really nice solutions and interpretation for these solutions. But what I want to show you here is what's the advantage of doing something like this, a more careful stochastic control. So here's an example where I used average cost values from the grid in California. And I imagine the cluster being the whole of our state. Okay, so one giant cluster. So we have about 60 gigawatt peak. And what this is showing in green is your 3 sigma rule. And in this axis, you can roughly interpret it as the penetration of wind. So this means wind is more than the peak load, and this means zero wind. And you can see here that the cost in dollars per hour per megawatt of the power is around $25 if you go by 3 sigma, which is exactly the estimated average cost per hour of power in California. Okay? Now this cost includes all those updates and the error forecasts and all that game that you played in the market. All of that is averaged and given to you. If you use our risk limiting dispatch, that cost falls down to about $4 per hour. Okay? So very simple stochastic control, appropriately using information and sensing, you can improve the performance of integrating wind, and moreover, you can design new systems out there. So just to tell you savings, if you have about 20% wind in California, that's about $272 million per year out of a simple change on the way we dispatch power. Now what I want to tell you is, okay, in our picture there, I said I have storage. So up to here, I didn't consider storage at all. I consider a cluster that was just load, some renewable, and the market. So now I want to add storage. But what is storage? Well, the way I understand storage is the following. It's kind of this virtual device. It may be a physical, actual storage device, or it might be some other things, which I'll mention to you. But the purpose of this virtual device is to be able to shift the consumption around so that supply and demand can be matched together more accurately. In that way, you can absorb some of your forecast errors or some of your dispatch decisions, okay? So that's why I call it a buffer, because this is exactly the role of buffers in the internet as well. They allow you to store information packets so that fluctuations on the rate at which you send packets over the network can be absorbed. Okay? Now, how can these buffers be implemented in practice? Well, you have fast and slow storage devices. An example of fast storage is just your lithium-ion battery-based EVs. You take a lot of them, you can very quickly charge and discharge power. Slow is your pumped hydro storage. But you also have other less usually thought about sources of storage. Forecasting can work as storage. If you are able to improve forecasting dynamically based on weather conditions or additional information that you obtain, you can make this mismatch more accurate, and that will translate to a certain amount of equivalent storage. Deferrable loads is also a form of storage. If I can schedule when you do certain things, I can consider that power consumption as energy that I stored and I released at a certain time. Okay? And demand response, where you go and control somebody's thermostat, can also work as a form of storage. So you can schedule when the thermostat is going on and off at a very high rate and try to match the consumption of that device to, your supply and to try to minimize this mismatch. And it's really interesting. There is a new literature emerging where this notion of a virtual buffer actually is applied across all of these different devices. Typical constraints that you need to watch out for, is obviously storage has a capacity. Deterministic capacity in these cases, maybe in the case of an EV, it's not deterministic. It depends on the number of cars that are available for you to charge or discharge. So it can be a stochastic capacity. Charging rate limitations, and as I said, availability. Okay. So keeping this idea in mind, one of the things we did was, if I added a storage to my cluster, can you give me a simple formula of how much improvement can I have? So I'm going to explain the formula. I haven't put the full formula here. So I have my cost of integration, which is kind of what I call here price of uncertainty. It's just a cost that only depends on the cost of power, so nothing to do with the resources themselves. And it's multiplied by this square root of sigma square forecast plus sigma square storage. What are these two terms? This term here is kind of the expected value of the slow error fluctuations. So when I'm doing predictions day ahead, hour ahead about my net load, I'm going to have a certain performance and error. Okay? That average error across your season is the sigma square f. Sigma square s is a different source of error. Now I look inside an hour, because these forecasts that are done a day ahead are done for a whole hour. Now I look inside the hour. There is these unpredictable fluctuations. These are super, super hard to predict. Today, there is no mechanism to predict them. So the grid is built to react to them. Okay? That has this standard deviation. So you have two sources of error. They're independent. You add them together. If you had no storage, your performance depends kind of in a linear way on the standard deviation, on the total standard deviation. So one observation is if I improve by 100% my forecasting, I'm going to get 100% reduction in the cost of integration. Now, interestingly, for storage, what it's going to do is going to reduce this guy. It's not exactly linearly, but as I make my storage capacity more or less of this size, square sigma s, I'm going to erase that number. So that's the benefit of fast storage. And we have various such simple formulas that you can use to evaluate how much potential there is for this type of issues. So here's kind of a curve of the cost and what happens to it when you have storage. In that same exercise, no storage. This is full, 100% of my peak load of storage. And this is just the cost ratio. So multiply this by 100. You can see even with very little storage, I already get a huge benefit here in the beginning of this curve. And about 25% of storage, I kind of flatten out the benefits I can get. And we see this across all these different settings people consider with power network, with multiple clusters that compete against each other, and so on and so forth. You can also try to look, as I said, to the penetration of wind power, which is kind of in a way the 1 over the sigma of wind, and just see that the cost is really indeed linearly related to the amount of uncertainty, even with storage. So here it's for fixed storage. You can do it and verify analytically as well as computationally. these issues. Now I decided to do another exercise. I said, let's forget storage for a moment and improve my forecast error. What happens to the cost? Again, if my forecast error reduces by 50%, I can go anywhere from $4 per megawatt or 3 all the way down to very, very small amounts. Okay, so this is just to show you storage can linearly decrease your cost of integration, but forecasting as well. So forecasting is an information issue. Storage is a physical device. So you can decide based on cost and availability of information what might be the best strategy, or maybe a combination of strategies to use. Okay. Then I did an exercise with deferrable loads. So we got load measurements for about 1,000 homes, and I tried to see how much can I follow different patterns of consumption based on scheduling these loads and allowing them to defer by just say 1 hour or 2 hours. So in an exercise here, for example, what we found is if you allow them to defer by about 1.5 hours, you get the equivalent of 40% storage. So it's the same as I'm giving you a battery that is about 40% of the peak consumption of your home, which is about 2 kilowatts. So you can take 40% of that, it's 800 watts. So that's a lot, right? Just for deferring or scheduling. Again, it's an electronic signal. It's not physically storing power. So what I wanted to go into, so you can do such exercises, build these models, and also study these type of controls and architectures. And as you try to implement them in practice, you have to start to consider more constraints and more detailed models. What I wanted to conclude with right now is kind of another dimension of this question, which is, what is the potential, if I'm a consumer, for storage and smart grid for me? So we actually got a lot of data from PG&E. We have data for about 400,000 households and maybe 300,000 small and medium businesses. And we can look at this data and do thought experiments of what happens if I add certain grid technologies, or what characteristics does the data give me about the customer. So here's one simple exercise. PG&E wants to introduce, it has already introduced what's called critical peak pricing. Very quickly, it means if you're a business, you will see a price for power changing over the day in a fixed way, announced ahead of time. And during the peak hour, you get an additive amount of cost for your power. Moreover, you have what's called a capacity charge, but I'm not going to discuss this right now. But now, clearly, if you have a situation like this, it makes sense as a business for you to have some storage, because you could buy the power here, store it, and use it during this time. And this price differential is tremendous. It's about 20 to 70%, depending on the pricing plan you take. Okay, so here's a simple calculation we did was, okay, suppose I have perfect forecasting, and I can move all my consumption from the peak to off-peak, and I have that price differential rho. So this rho is the price differential, that additional cost in percent. This is the total consumption off-peak, total consumption in peak. VS is kind of your percentage savings on your bill. Okay, so I calculated this number. I went through the data for customers in my database for about 4 years, 500,000 customers. And then I said, let me look at the distribution of savings in this very idealized scenario where they are able to buy a lot of storage. And you can see here in the more aggressive plan, they save on average 70% of their bill by using storage, or they can save about 20% of their bill. Now, why is this relevant? Well, because PG&E is proposing, starting next year, to give rebates for people to buy storage. So there's various mechanisms now where people are starting to think about giving access for end customers to these technologies. Now, the next question, though, as I said, if you're a consumer, I was assuming you had a perfect forecast, but that's not really true. You need to take into account the fact that if I'm going to operate the storage, I have to predict how much peak power I'm going to consume in the next day. So the first exercise to understand prediction for individuals, which is something extremely hard in power. So power systems operators have focused on predictions of groups of hundreds of thousands of individuals. So what happens when you have one individual? This is what your power consumption looks like. Here I added two together 5, 10, 80. Now you can imagine if I add 100,000, it looks very smooth, much easier to predict. This is super hard to predict, right? So if your prediction is bad, what's the point of buying that storage? Because you're not going to benefit from it. So we did a calculation, and we figured out the actual cost savings of having storage in your facility is directly proportional to your forecast error. And then the question I had was, what's the forecast error for one user alone? What's the forecast error if now I decide to partner up with my friend and we both buy storage but we manage it together? What is now maybe a cluster of 80 people? Okay, so we did this exercise across this very large data set we have, and here is the curve we obtained, which is really interesting. So what is this curve here? Here is the percentage forecast error on this axis. Okay, each dot here corresponds to a average forecast for a day. So I average across, every 1st of May and so on. And I used various different models. In this case, I'm using a simple AR model. And I'm just trying to predict a very simple prediction. I'm trying to predict my consumption an hour ahead. So here's an interesting thing. We as individuals, we are about 1 to 2 kilowatt hours in consumption. Forecast errors are around 100% relative error. So it can be 2x off. As you add 10 people together, it already falls down to 10%. And as you have maybe, 1,000 people, you kind of flatten out on the benefit of aggregating people. So what this curve tells you is, first of all, it's very important to aggregate resources in the grid, because only then you can do accurate forecasting. Here, it's really, really hard. But as you aggregate them more and more, I can predict this net load more accurately. And you can see this effect for predicting whether your air conditioning is going to be on, or whether you're going to, and other resources as well. But also, this aggregation benefit, it flattens out. So after a certain point, there is no need to be worried about aggregation. So this kind of flies in the face of the argument utilities give us for the way they manage power. Because they say, well, it's really hard to predict individuals, therefore I'm going to aggregate everybody. But what this curve tells you is it's sufficient to aggregate about 100 to 1,000 people. So you can form small clusters and manage them. Your performance is going to be as good as PG&E's performance in managing the whole neighborhood or whole city. And now we are seeing more and more cities and small towns who want to become their own utility in California. And they're thinking about how to build these systems, how to bring these insights and transform them into actual technology that they can use and manage their power consumption. So this is a very positive curve. Okay. We had a similar exercise for the impact of penetration of wind. And we found a very interesting observation. Typically, people have said, well, wind should be managed as a complete aggregate, and only when you have about 20-30% of penetration, it's going to have a huge impact in variability in the grid. That statement is correct, but the cost impact happens much before. Because the way the grid works today, you have a series of generators you use to dispatch and match your load. The last few generators, they're pretty small and very expensive. So if I add a little bit more of uncertainty in wind, I may have to dispatch these last few more often. So my power cost rockets up. So again, even at moderate or mild penetrations of wind, you have to be clever about the strategies you're going to use, and not necessarily it's the best idea to aggregate all the wind, aggregate all the load, and manage it all in aggregate. Okay? So this is just a few conclusions here for you guys to remember. One, smart grid is really control operations and the architecture that you're going to utilize for these operations. Second, storage is one example of buffering. And I think in this new grid out there, buffering is the most fundamental concept. Being able to buffer and model this buffering in various ways. You can model it analytically to get some insights for planning or for policy, but you can also model it in a very physical way to get actual systems that you can manage. And three, the importance of clustering. So definitely you want to aggregate resources. Maybe you don't want to aggregate them a whole citywide, because first of all, it's not manageable to enroll everybody on the programs you want. Second, not everyone will contribute equally. And third, we saw that the benefit flattens out after about 100 or 1,000 people. So you can start thinking in a completely different way and out of the box. Don't have to be constrained by the way power systems people think today. So if you really want to redesign the grid, we need to fly away from that and start using these insights. And the fourth thing I really believe is the importance of data. So we have been doing a lot of work with data from smart meters, but data is going to come at various resolutions, and it's going to affect tremendously how we manage the grid. Okay? So thank you very much. Yes?
When you were talking about the uncertainty of wind and the impact of that on cost, does that also apply to solar?
Yes. In fact, when you think about smart grid, you can think that solar and wind are more or less the same beast from the point of view of uncertainty. The difference that's going to happen is the magnitude of the uncertainty and perhaps the uncertainty model you use. But the way they will influence your control is very similar. Okay? Yes?
So you pretty clearly showed that it's difficult to predict one person's behavior, like a very small group. And so it's not economical for them to pursue storage in very small groups. But is it possible that if they know that making their behavior predictable would save them money or would be an economical source, that they would actually become more predictable and so be able to?
Yeah, that is possible, but it might require a lot of change on their part. It might be even more possible if you provided a platform where they could hook up the resource that they got for themselves and you guaranteed them a return, they will be willing to acquire and invest on that resource. So if you offer people and say, look, I'm building a little cluster around Palo Alto downtown, and people who have solar come into that, people who have storage come into that, and I'll manage these resources for you, and I'll give you savings which are much higher than what you would obtain if you only use your own resource for yourself. So that is also a potential possibility. So you can either change the behavior of the person or use the fact that across multiple people, on average, we behave the same. Okay, and try to, yes?
Building on the question before about solar power, we've seen a lot of government policy, especially in Europe, where there's a push that people put a lot of solar panels on their roof. Mm-hmm. Judging from your conclusions, would you say that that is inherently a bad policy because it will reduce cost?
Yeah, so the reason why there is a push, a positive push, if I'm interpreting correctly, is, okay, they want to make their grid more sustainable and more renewable and move away from nuclear nowadays. That's their big thing. But they also have a pushback, because what they're observing is when there is high production of solar, utilities are disconnecting certain panels at the end of the feeder who end up affecting the grid the most. So there is this balance. What I feel is if you allow people to aggregate around local resources and self-balance power, it makes a lot more sense for you to now have a solar panel, because you're not dependent on a policy from the government that says, I'll help you out and give you some benefits financially every month or so on. You might just be able to make your money off of balancing your neighbor's consumption of his EV. So your EV plus the solar, they match up nicely. The losses are very small. So if the loss is coming all the way from the head of the feeder to your home, it's about 20%. Okay, you could avoid all of that if you're consuming your power locally. Okay, so there's a lot of room for those ideas, but people haven't really explored those. Part of it, I feel, is when we are young researchers, we're sucked into thinking in the same exact way this very old field has been thinking about. But I think now we have data, we have so much information, we should be able to consider these new models better. Yeah.
Thanks for taking my question. Could you just comment on the use of, renewables, which are inherently intermittent, kind of being viewed as a bundled set over a large geographic area being used for baseload power stores?
Yeah. So there is two aspects to this question. One aspect is what I call resource availability. Those are the kind of studies Mark has done and shown the potential for a bundle of renewables really matching up the needs of loads. If you're in the power systems operations now, there is a whole host of other issues that you need to take into account. Fluctuations in the very short time scale, unpredictability, because even if I look at the data for 1 year, maybe there will be events that I haven't captured. And considerations across the network, like voltage levels, phase angles, etc., congestion on your transmission network. Once you put all of those things together, that's what I call the power systems operation aspect. And if you want to consider, okay, what is the impact of renewables as base load, even if I just put wind, there is an impact as a base load, but it will depend on what are my backup power options, what are the strategies I have with customers, do I have DR, do I have direct load control, or is it the load control is indirect or prices, and moreover, what's happening in terms of voltage control in the grid, etc. So, yeah.
A lot of the benefits that you were talking about with storage of various types comes from time of use pricing. And in many areas, time of use pricing doesn't filter down all the way to the end user.
Mm-hmm.
So what are the industries, geographic areas that you think have the best potential given their current time of use configuration?
So right now, time of use pricing is becoming the norm in Texas and in California for small, medium businesses and large businesses. So that's already a big opportunity because these guys don't really have the resources to optimize their consumption. In the future, maybe utilities will offer these plans. But I really believe in the future, we will have guys who manage power locally. So these might be new entities, aggregators or local utilities, who then can design plans, or they might be able to say, I'm not going to offer you pricing. Actually, I'm going to use these resources to match supply and demand and give you a fixed cost for your yearly bill. So it's completely predictable for you. So people have been studying these type of models, and I think we are going to start to see more and more of them as we get a little bit of deregulation, as well as intellectual firepower showing that these things are beneficial. Okay. I think maybe one more question? Okay. Yeah.
So I was wondering if you could give a sense of how the monetary benefit of putting storage in a right size cluster to manage the variability compares to the cost of the technologies or the measures.
So you're talking about the return on investment. I haven't done that calculation. We are actually now in the process of gathering some data to look into that issue. This is my feeling. There is certain types of storage which are lower initial cost and maybe higher operating cost, which will match up very well with the situation we have today. But if you become very aggressive about the penetration of solar and when maybe some other opportunities open up. So here's my thinking on planning. Actually, last week I was having a discussion at Berkeley exactly about power planning. The way power planning is done today, it takes a very detailed model of the existing grid, looks into the past, and tries to replicate what happens in the future when you add new technologies. But for example, all the power plans of 10 years ago all turned out to be wrong because natural gas is super cheap and solar prices have come down drastically. So whatever you planned with your very detailed model is incorrect. So what I feel is when we start to ask these type of questions, we need new planning models. These planning models are not accurately replicating the operation of the power grid, but they should be able to capture some of the basic conceptual benefit of storage with some simple formula, but also incorporate kind of the uncertainty on various scenarios you have about cost. Because I can't imagine 10 years into the future, these batteries have already reduced price 10x in the last 10, 20 years. It's not going to be constant. So that calculation we can redo. But my feeling right now is only the more traditional types of storage are viable in large scale. Okay. Thank you very much.